Welcome to ExplainerCast, episode 15. I'm your host, Dave Smith.
And this is Shane Swenson.
Today's episode is a continuation of our telecommunications explainer series, where today we're going to talk about the domain name service, commonly known as DNS. And just to kick this off, I want to introduce why this exists. And I think a good way to explain that is to say, well, for the past, I don't even know is this our 6th episode on telecommunications?
Yeah, I think so.
For the past 5 episodes, all we've been talking about on the internet are IP addresses and messaging. So we say, hey, if a computer wants to send a message to another IP address, this is how it happens. But hopefully someone by now has noticed that when you use the internet, you never, ever type in an IP address unless you're in that frustrating time of life when you're configuring your home router that you just pulled out of a box. But aside from that, we just don't use IP addresses day to day. And so this is where DNS comes in.
Yep. And this goes back to, I think, even in the 1970s and 80s, as soon as the ARPANET was starting to have more than a few computers on it, people quickly realized that they thought about these computers based on maybe the institution they were at, what educational institution or college or university they're at, or, some other identifying characteristic. And sure, they had to have a number for even the ARPA protocol, but humans we think in names. We don't think in numbers. And so in the very early days, people would write these down, and maybe initially you'd start with a notebook and you'd just write, okay, that computer at UCLA, here's its ARPA number. The computer at Stanford, here's its ARPA number. And eventually people said, well, let's put this into at least like a file, a text file, so that you could have software that would check the text file for you. And eventually the internet really outgrew that text file and became this system, the domain name system. And Dave, you call it domain name service. I actually call it both. There's so many different interpretations of many of these acronyms in technology land. So we'll call it the DNS. We'll probably call it either the service or the system, depending on how we're speaking about it.
Sounds good. I fully accept either versions of S. And I'm trying to think of a funny third option for the letter S. Sasquatch? I don't know.
Domain name suite. Anyway. But yeah, so unless you really are deep into network configuration, it's very uncommon to be directly interacting with the numeric addresses that are used to actually route the messages through the network. And so today we'll go into some detail about how the DNS provides that mapping between names that we humans understand to the numeric addresses that the computers need to send messages to each other.
Which seems like it ought to be a pretty simple problem. It's like, we just need essentially like a phone book for all the different addresses out there. But, this is computers, so everything is about 1,000 times more complicated than you think.
Right. And it starts simple. Like I said, in the early days, it literally was just a file. And then you could pick up the phone, you could call the administrator, and they could add your entry to the file, and then they would basically like file transfer or email it out to everybody. And so there are really two basic problems with that model. One of them is scale. Today, there are billions of computers on the internet, so that's a very big file. But two is one of the goals from the early days of the internet was to decentralize as much as possible when it comes to the administration of the network. And so everybody having to go contribute to this same central information repository, even if it was a database instead of a file, still just fundamentally didn't align to really the values of the day. And so one of the beautiful things about the DNS is they found a way to distribute it and decentralize it so that I can be responsible for my portion of the namespace on the internet. You can be responsible for your portion of the namespace on the internet. And we actually don't have to coordinate with each other very much. And furthermore, we can also decentralize the servers and the service side of it so that at internet scale, it can still function. Because imagine if there was one poor computer somewhere that had to resolve all DNS queries all the time. And we'll talk more about what that means. But just imagine if everybody on the internet was asking the same server, what is the address of Google's server right now? That poor server would have no way of keeping up with the current traffic load. So The highly distributed nature allows it to scale, but it also allowed it to be administratively managed in a decentralized way.
And that is so interesting because I often wonder, what were the motivations for this distributed management of the internet? And I have to think there were probably some kind of philosophical motivations. Like, we got a bunch of engineers and none of them want to be in charge. They're
Yeah.
like, okay, how do we build a system where none of us have to be in charge?
Yep.
DNS comes from that. But also, the internet grew so fast when it really started to pick up steam that realistically there was no way for any central organization to manage that and actually let the internet grow at the rate that it was pressuring the growth to happen.
Yeah, I would guess that being in the position of a centralized administrator became immediately so overwhelming that you couldn't get rid of it quickly enough. But this was also...
Quick, design me a distributed solution.
That's right, exactly. So I don't have to do this anymore. And again, think about, this is the US in the 1970s. I think there was a lot of anti-authority just vibe, especially on college campuses. And I think it's hard to overstate how much a culture and people's values will actually influence even their rational design decisions about something. So I sometimes feel like the internet kind of reflects, again, the culture and the values of the time and the place of the people who are building it.
Yeah, for sure. So
with that as the preamble, I guess let's talk about how this works in practice. And so I think let's start with just, again, we kind of motivated. Let's start with, how do we get a name that we even want an IP address for? And I think probably the most common use case these days would be in a web browser.
Yeah, I think so. Although, there's a lot of devices on the internet now, like a lot of cars, ovens, phones, and even the apps you use on your phones are using DNS. But still, like, as a user, you're right. Like, that's when you're going to interact with DNS and actually see the direct result of a DNS thing happen when you type an address into your web browser.
Yeah. So let's motivate that. Let's use that example, and then we can talk about some of the others too. So yeah, when you load up the web browser, essentially it, in its default state, is going to show up with nothing or maybe some homepage. And so we as the user are going to choose what service we want to connect to. And as everybody pretty familiar with, I assume, listening to this podcast, you go to the address bar and you actually can put an IP address into that address bar. It doesn't work so well anymore because it turns out the web browser and the web server need to know a little more about what you're trying to do. But it used to be pretty common that, like, say in the 1990s, like, you want to go to a website, you could just put the IP address directly in. But today, what we're going to do instead is we're going to type in the name of the service we want to connect to. And so that might be, again, for example, like a google.com or something like that. And historically, the idea with the early web was that name would, in fact, be the name assigned to a particular computer connected to the internet. And then the web browser's job was to go to that computer and load the web page. And so the first thing the browser has to do is take the name you gave it and identify the IP address associated with that name. And it's going to do this using a mechanism called address resolution. It's going to resolve the address, specifically the Internet Protocol address associated with that name. And it's going to use the DNS to do that.
Yep.
So typically on your computer, well, I guess on any device, mobile phone, etc., car, you name it, there will be a piece of software that understands how to use the DNS. And so the web browser will take that name and essentially it'll use that software running in the operating system on that device and ask it to resolve that name. And then that piece of software is going to reach out through its connectivity to the internet to perform the address resolution.
And I think I just want to jump in here and say there's a bit of a bootstrapping problem here.
Yeah.
Because I guess maybe I'm jumping ahead too much here, Shane, but how does the DNS system in the browser actually know where to go find the name resolution for the host that you typed in?
Yeah. And there are actually, I think I know of two different answers to that question. And then after we talk about this, let's talk about the structure of the names. So one answer to the question is when you connect a computer to the internet, often there are a few pieces of information that are required for that computer to function as you expect it on the internet. It has to be given an IP address so that it can communicate with the other devices on the network. It needs to be told usually some information about the router it's going to use to connect outside of the local network to the internet, often called the gateway router. And it's pretty common for it to also be told, here are the IP addresses of one or more DNS servers that you can use for name resolution. And those might be servers that are resident on the local network, maybe like in the home router, for example. It'll nominate itself and say, I can do DNS resolution for you. Sometimes the internet service provider has DNS servers that it manages, that it gives to you. Sometimes the network administrator has a particular set of choices. So that's one way to do it. The other way is that the entire domain name system is itself a hierarchical database. And if you know how to communicate to the root servers of that database, you can then find everything you need. And so to make more sense of that, we really need to talk about the structure of the names themselves, though.
Yes, makes sense.
So, Dave, give me an example domain name that comes to mind.
Well, I'll just give the very first domain name I ever typed into a computer.
All right.
I can still remember. I don't know. I actually don't even know what year this was. It had to be early to mid 90s, but the very first domain name I ever typed in was digitalcity.com.
Nice.
I don't even know. I wonder what it is. Let me go. I'm actually reluctant to even look this up.
Yeah, who knows what it is today, too.
Yeah.
Decades later.
I just remember it had like a cheap graphic of a city kind of in digital form. Oh, the site's not working anymore. No. Once upon a time, digitalcity.com was a website you could type in.
Nice. Yeah, I'm thinking of
All right,
early
there's your
ones.
Example.
Like, yeah, early ones for me were like yahoo.com or webcrawler.com. Trying to
AltaVista.com was a fave of mine.
AltaVista. So in each of these cases, these names have a name that we recognize followed by dot, followed by com. And that structure is important. And we're just kind of used to it. And so when you talk about .com as if it's just English these days. But when the domain name system was developed, the idea was that names would have a hierarchy. And so there were a set of what are called top-level domains like .com, .edu, .net, .gov, and others. And then those domains, those top-level domains, could then host subdomains. And so digitalcity.com represented Digital City was a subdomain of the .com top-level domain.
Mm-hmm.
And so all domain names have some type of hierarchy. They don't have to end in .com. They can end in other top-level domains, and they can have more than 2 levels as well. So, for example, going to a more modern example, you can connect to something like mail.google.com. And so mail is a subdomain of Google, which is a subdomain of the .com top-level domain. And the idea with this hierarchy is then you could do 2 things. Number one, you could, as you build out the hierarchy, you can delegate responsibility or delegate authority for the administration of subdomains. So for example, at the very root of the entire system is what's essentially called the root domain, which is something we never type, but essentially there's an implicit dot after the .com that represents the root domain. And that is actually managed at the internet level. And so it's the most centralized thing. It's kind of the thing that everybody on the internet has to agree exists and represents the root of the domain name system. And then below that, each of the top level domains like .com, .gov, .edu, etc., can actually be managed by a different authority. And then below one of those, like say below .com, each of the subdomains can also be managed by a different authority. So for example, Google has registered google.com, and they can then manage google.com and any subdomains they want to allocate in that domain name space. And in the case of digitalcity.com, somebody would have registered that. And then I don't know what it was, but let's say it was a site that you could create subpages on. They might allow you to create dave.digitalcity.com, and they could even delegate that to you, and you could create whatever names you wanted below that. So with this relatively small amount of root level coordination and governance, this system allows for really the entire Earth's population and nations, countries, and other organizations to each have their little slice of the domain name system and then manage it according to their particular needs and usage. The other thing this enables, or go ahead.
But before we go on, Shane, you mentioned that Google would have registered the name google.com.
Yes.
Who would they register that with, and where does that information reside?
Yeah, so there's an entity called the Internet Corporation for Assigned Names and Numbers, and they now run essentially the top level registry. It used to be that it was the U.S. government back when the U.S. government was funding and subsidizing a lot of the development of the internet. It actually rolled up to the government, but now it's this independent corporation, and they manage, again, the very top level. And then there are a number of companies who manage usually the next level down. So I forget who currently administers .com. I know it used to be VeriSign. And so they, again, have authority.
Looks like it still is.
Okay. And so they have to follow some governance rules, but you would register with them, and usually you pay a fee. You might have to, in some cases, prove some right to the name that you're choosing, and then they would delegate further to you, and they'll put that information in a database. Now, it's more and more common for privacy reasons, to obfuscate some of the registration information in the database. But it used to be that it would list like the name and address and contact info for the individual or organization who performed that registration, again, so they could be contacted if needed.
So now I might get a little bit ahead of ourselves here, but this is how your computer ultimately is able to query what is the IP address for digitalcity.com. But I'm not quite clear on the process, and maybe we'll get to that in a minute. But essentially, before we go there, the delegation of authority is, well, there's an implicit dot that has the root servers for all the DNS for the root level.
Yep.
They tell you, okay, for .com addresses, you need to go to this DNS server. And then it's like, okay, great. So you go to that DNS server and say, all right, well, for digitalcity.com, what's the IP address? And then it'd be like, well, you need to go to this DNS server for that. So essentially, these clients kind of get bounced around. Am I saying that right?
Yeah. And you've jumped a little bit, and that's fine. I was talking kind of in the abstract from like a authorities standpoint, like who has the right to define what's in each of these. But you're absolutely right. There's a parallel structure, which is that each of these different entities can actually run their own servers. And so the result is that there may be no single server that has all the answers, and they have to work together to deliver that answer. So let's talk about a couple different components in the system to get there. So on your device or your computer, you have a reason you want to get, say, the IP address for a domain name, and you have a local resolver, which is just a piece of software that knows how to use the DNS to do that. And it perhaps has the IP address of a DNS server that it should make use of, like I said, assigned by the ISP or the local network. And typically, that DNS server that you're going to connect to is what's called a recursive resolver, because it is going to essentially work its way through the network to find the answer. And so your local resolver is often very simple, and it just wants to ask a question, get an answer. And we'll talk about exactly how that works shortly. But this next resolver that it connects to is what's called a recursive resolver. And think of this as like, this is like the buck stops here. I'm going to get an answer no matter what. And the goal of the recursive resolver is to find what's called the authoritative server for that particular name. So for example, if it's digitalcity.com, it might need to go find, well, where is digitalcity.com's name server? It may not be hosted at the root. It may not be hosted at .com. It may be somewhere else. And the way we do that is we first ask the root, can you give me digitalcity.com? And the root is going to respond back and say, no, but here is a server for .com, and essentially go ask them. And then that recursive resolver will take that answer and go ask the .com authoritative server and say, do you have the IP address for digitalcity.com? And that server will probably reply back essentially saying, no, but here is the name server for digitalcity.com. Go ask them. And now the recursive resolver can actually connect to the name server for digitalcity.com and say, what's the IP address for the digitalcity.com web server, say, and then get that actual IP address back from the authoritative server. So essentially it recursively, meaning it tried and then it tried again, worked its way, it actually iteratively worked through each of these different servers in order to give the proper result back. We call it recursive because it was doing all of this because somebody else asked it the question. And rather than just giving a quick answer, it actually went and then asked a series of questions of other servers. So that's the recursive step in order to find and deliver the correct answer. So to summarize, we had a few different, really, computers all involved in this one thing we're trying to do, which is we just want to know what's the IP address of that web server or that computer that we typed in. And our local device had to initiate the transaction, the lookup. And again, it often has a thing called a stub resolver to do that, which is a very simple piece of software that just knows how to ask the question. And typically that query, that question will go to what's called our recursive resolver, which is going to take our question. And for now, we assume it doesn't actually know the answer. So it has to go out and find the answer. And it's going to make a series of additional DNS queries to do that. And those DNS queries, you asked about bootstrap information. The one thing that recursive resolver has to know to be successful is how to find a root server. So it needs to have one or more IP addresses. It can't have names because the names need to be resolved to IP addresses. So it has to start with the IP address of one or more of those root servers. And then it can start from that point and then iteratively work its way down the tree or down the path to the authoritative server for that particular domain. And as it does this, the other thing that recursive resolver will typically do is it will store the answers it gets in a cache, which in computer science means a temporary store of information so that you don't have to go back to the authoritative source next time you need it. And this is part of what allows those root servers to even survive, because the sheer number of queries taking place these days has got to be absolutely enormous. And the root servers see a lot of that, but they only see a fraction of it because most of the domain name servers along the way are performing caching operations. So the next time we ask for this same query, that recursive resolver might actually have the exact answer in its cache. It might say, oh, here's the IP address for digitalcity.com, but it almost certainly has the .com name server in its cache and wouldn't have to ask the root server for, say, .com again.
Yes, and that is why every DNS query isn't immensely slow, because it doesn't have to actually make the way all the way up the path to the root servers.
Exactly. And a couple other really small things just to point out, because if you think about what I said very carefully, you might see a problem. And so I talked about, as we recurse down, let's say that .com server says, I don't have the answer for digitalcity.com. Here's the name server to go contact. One question would be, well, what format does it give us that name server's identity in? Because if it gives us its name, who am I going to ask to resolve the name? And in fact, it will give us a name, but it usually is configured to also give us the IP address associated with that name immediately in what's called a glue record, which enables you to actually traverse down the tree, because you ultimately need the IP address of digitalcity.com's name server in order to send it the query to find out what its IP address is for its web server, digitalcity.com. And the other piece you could say is, well, then if you know that, don't you already know the answer? And the reality is that often the name servers are hosted on different servers with different IP addresses than, say, the public website for, say, digitalcity.com. So those name servers might have a name like ns1 and ns2.digitalcity.com, and that's actually what the DNS will point to. And then when we ask them, okay, what is the digitalcity.com IP address, they'll give us back the web server's IP address in that subsequent query.
Something tells me that digitalcity.com was not a sophisticated enough organization to have its own name servers.
Yeah, if we're talking mid 90s, it was probably all one computer, but
yeah.
not anymore.
Yeah. And it probably delegated the name servers to whoever they registered their domain name with, who those registrars tend to operate name servers for you.
Yeah,
so you don't have to do it.
That's right. It's very common now to just let them handle it or let your web hosting company handle it. So there is a lot of consolidation, but the architecture does enable every one of these entities to be a different server or service, running on different computers with their own IP addresses.
Okay, so we have a distributed hierarchical database that can be queried at any of the levels in the hierarchy.
Yep.
And its contract is that it will either give you the answer or tell you who to go to get the answer. And you can just keep querying until you get the answer you need, which ultimately you're just trying to get an IP address if you're trying to go to a website like digitalcity.com.
And one other thing, it can also tell you, I don't know. Like if you ask for something that isn't listed, then you're done.
Or a non-existent domain name, right?
Right.
It just doesn't exist.
Yeah, exactly.
So it needs to be able to support that. That's just as valid of a response as here's the IP address.
Yep.
So I want to take if it's okay, I'll just take a minute and explain a different angle on this same thing, which is if I want to go set up a website on a new domain that doesn't exist yet, how do I get my website enrolled into this system so that other people can type in my website name and get a valid IP address and go? Well, maybe I'll just briefly summarize how that works.
Yeah.
Which is you go to one of these registrar companies, which Shane, you mentioned are delegated authority from the ICANN, the Internet. Well, what is it? The Internet
Corporation for assigned names and numbers.
There are many companies like this that do this now, and they'll charge you somewhere between $5 and $5 million, depending on how valuable the domain name you want is, for the privilege of registering it with them. And then they'll give that name to the ICANN. And then also, most of these registrars, which is what they're called, will operate DNS servers.
Yeah.
And what's really cool is that when they register your domain name with the ICANN and ultimately into the hierarchy of DNS server names, they will also register their DNS server names as authoritative for that domain. And this all happens behind the scenes when you register your domain, but it all happens so magically that when someone actually tries to go to your domain, it all just works.
Right.
But that all has to be part of the job of a domain name registrar.
In a modern sense, I agree, because that's what the customer expects. And so, when you sign the agreement or the contract, you could say essentially, yes, I want them to be your DNS provider. And so you've then granted them your authority to act on your behalf. And then they'll say, yep, their name servers are authoritative for your domain. On the other hand, you could say, no, I actually want to run my own, or I have this other hosting I want to use. And in that case, you'll have to give them some additional information. You'll have to give them the names and IP addresses of typically at least two name servers, an authoritative like primary server and then a secondary as a fallback if the primary is unreachable. And then they'll put those entities into their system, into what's called their zone, so that when that recursive resolver asks them for your domain, they can return that response back, allowing someone's recursive resolver to then find your actual authoritative server and make the correct query.
Exactly. And that's why you can't just set up a website without using one of these registrars who has been authorized to update the ICANN database in the hierarchy.
And I would say,
in fact, Shane, it's
just a little semantics there. I would guess that when you say update, I guess they have to maintain a list of who's registered. But I would guess that ICANN actually has delegated to those registrars to maintain those databases, both call it the public entity, like what's your name and address and contact info in the real world, as well as the DNS server registrations. So I don't know that you're updating like the ICON database itself per se, as much as you're updating this delegated thing that is referenced through the ICON system. Does that make sense?
Interesting. Yeah, I wonder if these registrars actually replicate information with each other. I mean, they must, because ultimately you can ask any registrar if any domain name is available for purchase, and they'll all give you the same answer, right?
Yeah, so they're at least caching all that information. That's true.
Yeah. And it's a fun throwback because it was about a little over 20 years ago that I registered my first domain name. And indeed, I did exactly what you described as that secondary option, which is I had to go find a DNS provider that had, at the time, a free option because I didn't have any money.
Yeah.
Like all I could afford was the $8 a year registration fee.
Right.
I couldn't afford to pay a DNS provider. So I had to go sign up for a free account with a DNS provider. And then I also registered my domain, which did cost some money. And then I told them, okay, here's my name servers. And it was actually pretty cool process to get familiar with how all that works.
Yeah. Yeah. And I guess while we're talking about authorities, there's probably one other important thing to mention, and that is that there are really two types of top-level domains. So there's one root at the top of this whole thing. There are many servers that serve identical copies of the root, so you can ask any of them. But then the top-level domains, the original top-level domains were these like .com, .edu, .net, .gov, .mil, probably a couple others I can't think of right now. And you can kind of see that was a very like America-centric view of the world. Like it was our government, it was our military, and .com in a way implicitly was kind of in the U.S. And so then, in addition to those, what are called generic top-level domains, every country on the planet has its two-letter country code top-level domain. And so when you see these two-letter top-level domains, and some of them conveniently, look like nice things to English speakers in particular. So, like .tv for television-related content, .ly if you want to make something look like an adverb or make it kind of look cute.
Yeah.
.io if you want to kind of be more like, networky, input outy. Each of those are actually country codes. And so some of those countries have found that there's actually a significant source of revenue. So like .tv, do you know where that is actually, what the authority is for .tv?
It's not Taiwan.
No.
Not Thailand. I don't know.
It's Tuvalu. It's like a country out.
Wow.
It's like a Pacific island country that, doesn't have a huge population or huge economy. And my understanding is that domain registration fees are actually a notable part of their economy at this point.
That's interesting.
And so those countries.
Well, I do know. I do know that Ireland has .ie, and I know that at least 10 or so years ago, when I was trying to register a .ie domain name, they had very strict rules, and you had to be affiliated with Ireland in some way in order to get the domain. And I did not get the one I wanted, so that failed.
Yeah. So again, and that points to, in the case of the country code top-level domains, the government of that country has the authority to set the policies by which you can register names in that country. Now, the servers might be hosted elsewhere. They may have delegated the technical responsibilities, again, to a VeriSign or somebody else, but they actually get to set the rules, and they get to collect at least a portion of the revenue. And so when you look at like .ly, that is Libya. And so some companies that have used .ly have in some cases chosen to stop doing so because they didn't necessarily want to, fund government operations there. So anyway, it's just worth being aware of when you see those country codes. You're not going to a service in that country per se, but in a way you're doing something that is at least indirectly, under the responsibility of that country.
Very cool. Okay. Where do we go from here?
Let's talk about one or two other things. So one of them is, we talked about queries and responses. And in prior episodes, we've talked about how to send messages from clients to servers using IP packets, using source and destination IP addresses, and using transport protocols like TCP and UDP. And so let's frame DNS into that context. So what protocols are the DNS going to use to send messages between the computers?
Well, any protocol you like is the correct answer, I believe.
Sure.
But the predominant protocol is, interestingly, it's UDP over IP.
That's right. Yeah. And why do you suppose they chose UDP instead of TCP? This seems like something we want to make reliable. So why would we choose UDP?
Yeah, I've wondered this, and I actually don't know the definitive answer, but if I had to hazard a guess, I would say it's because they didn't want to pay the latency price of the TCP three-way handshake just to get an answer for a DNS query.
Yeah.
And this is particularly important because DNS tends to be the gating activity that happens before anything else can happen with an online interaction. And so they wanted to minimize the time that you would spend waiting for DNS results.
Yeah, I think that's exactly right. And I'll flip it and I'll say, if you're implementing the DNS server and you're using TCP, you're going to receive you have to do the full three-way handshake. You have to reserve memory buffers, and you still haven't even found out what the query is. And on the other hand, if you're using UDP, you receive a message, you look up the answer in your database, you send a response, and you forget that it ever happened. And so
so it's extremely stateless. Like we talk about stateless protocols. This is super stateless.
Yeah, this is as stateless as a two-way protocol can get, basically, a request response, where get a request, send a response, move on. And so it makes the server very low cost for a given volume, or to put it another way, very highly scalable and highly resilient against very large volumes of traffic. And so it's ironically, by using what appears to be a less sophisticated or less reliable protocol, we actually get a more reliable system, because most of the time that query message is going to get through, that response is going to make its way back, and everybody's happy. And in the case where something goes wrong along the way, then on the DNS resolver can just ask the question again, can just send another message re-requesting, the whole question without trying to use the TCP, retries and reassembly and so forth. Having said that,
I wonder, Shane, do you know if these DNS clients tend to do any kind of congestion control or prevention from flooding the network?
I don't know. Yeah, I don't know if they would have any back off. Typically, there's a concept, and you talked about how you've got an impatient user like waiting for this to happen so they can even go, so their browser can go to the right server to request the web page. And so in the search for what are called happy eyeballs, often these protocols will be pretty aggressive. They might even send out multiple queries in parallel to different servers to see who gives them an answer fastest. And I don't know if that's a common practice, but it's definitely one that people consider when they try to make these more reliable for very fast turnaround.
Yeah.
But you shouldn't have a lot of DNS traffic per client. And then that first level recursive resolver, if their cache is working well, a lot of the requests are going to be answerable out of that cache as well.
Yeah. And I don't know if now is a good time, but there is a lot of caching that happens at lots of different layers.
Yeah.
Should we go into that now, or should we pick that up later?
No, yeah, let's go into that. So yeah, you want to describe some of those layers?
Yeah, like when I think about all the caching that I've had to deal with, because this is actually kind of a painful thing too.
Yeah.
When a particular entity in the DNS ecosystem caches for too long, it can create real headaches for people who want to do things like move my domain name from one web server to another or from one hosting provider to another, and that just doesn't take effect immediately. So first of all, most web browsers, or at least the most popular web browser on earth right now, which is Chrome, actually has its own DNS cache built into the web browser itself. That's independent of the operating system, which also might have its own DNS caching as well.
Right.
Which in the case of macOS is also true.
Yep.
And at least in the case of my home internet, my Wi-Fi router is also a DNS server, and this is a very common pattern for your Wi-Fi routers.
Yep.
And it has a layer of cache.
Yep.
So here we have, before the packets have even left my home, there's already 3 caches that DNS has encountered.
That's right. And they're all just there to make it faster and to save maybe a little bit of traffic, but mainly just to speed it up so that you are happy as the user.
Yes.
And then, into the infrastructure on the internet side, there'll be caching often at the different layers there as well. And so an important property with caching is to know how long that data is valid for. And so in DNS responses, there is a time to live value, which is supposed to tell everybody who caches this is how long you can cache this for. And so there's a trade-off in, do I choose a long time to live, which means you won't come back and ask me the same question very often, or do I choose a shorter time to live, which might mean the authoritative server has to respond more frequently to repeated requests, but it gains the benefit that it can make changes and they'll propagate through the system more rapidly as those cache entries expire.
And specifically changes to the IP addresses that are associated to a specific host name.
Yeah, exactly. Like if I want to, that's the most common case would be, right, I want to change that IP address and I want to make it something else. And so I can publish the change authoritatively, but for some period of time, due to all those caches, lots of clients will still be hitting the old address. And so I have to keep that one working until the traffic has essentially drained from the old one and then it goes to the new one.
It really is painful. And I'll tell you, having led an engineering team that migrated an entire web application from one cloud provider to another cloud provider and having to rely on that DNS propagation. By the way, that's called DNS propagation delay.
Okay.
Having to rely on that, you can spend hours, days, or weeks waiting for all of your clients to actually move their traffic over to the new IP addresses, because it turns out, even though your DNS record will say a time to live, it doesn't necessarily mean that all clients will honor that. And some clients will just presumptuously choose a longer time to live because they favor user speed.
Yep.
They favor low latency resolution over your ability to change your IP addresses.
Crazy. And yeah, there's nothing you can do about it.
Nope. Yeah, it's just how the internet was designed. It's kind of just one of the trade-offs of having a highly distributed system.
Yeah. And another a use case that's becoming more common is that with some of the global internet services, there might be lots of servers in lots of data centers all over the world that provide that same service. And so when the DNS was first developed, it was really giving names to computers. So the computer would have an IP address, and now the computer also has a name. And with large-scale web service delivery, typically a service will now be hosted through lots of computers, and often for reliability and performance, those computers are even in different parts of the world. And so one of the questions is, well, how ideally each client and each user is directed to an instance of that service, a computer is serving them that's close to them. So they have a fast response time, a high performance response, and it's actually a little cheaper from a service delivery standpoint as well if you're not traversing as much infrastructure. And there are a number of techniques that can be used to steer different users to different service instances, but one of those techniques that can be used is a more dynamic DNS response, where depending on where you are in the world and which DNS servers you reach or which IP address the query comes from, that DNS server may give a different answer where it's trying to steer you to what it thinks is going to be like a local data center hosting that service. And in even the more extreme cases, that might even be dynamic based on load, in which case they'll want to use a relatively low time to live, like maybe measured in minutes instead of measured in days, so that they can sort of start to move traffic in a different direction if operations demand that.
And then they just hope that all the clients adhere to the TTLs, which they largely do, but
And not everyone's going to listen, but if like enough do, you can still kind of have an effect on the movement of the traffic. And again, these are pretty aggregate concepts.
Which is really cool. I don't know if you said the word content delivery network, but that is like the number one killer app use case for this distributed, dynamic DNS. Dynamic DNS isn't even the right term for this, but I'll just call it like geographically sensitive DNS resolution.
Right.
Where the DNS server can say, I see that you're in the state of Texas, so instead of resolving the digitalcity.com to the IP address that I know is in Virginia, I'm going to resolve it to the IP address that I know is in New Mexico, which is closer to you.
Yep.
And so you'll get a faster experience for the same web application, which is really, really darn cool.
Yeah. Yeah. And quite a few steps removed from where we started in this system, but yet that is what what people are doing today.
Isn't that just the sign of a really well designed, a really well architected platform that fast forward, 40 years, and people have adapted your platform to do just amazingly hard to predict things that no one would have anticipated.
I think it is. I think it's pretty remarkable how the basis of the protocol hasn't changed very much. And yet these new use cases can be added in and done so successfully. And it's this, there's something really unique about the way the internet in particular was architected. This is another example of a form of intelligence at the edge, because the authoritative name server, in a way, is kind of at the edge of the network, and we're reliant on all the routing and connectivity to get messages to it. But we're also even reliant on this hierarchy of authority and delegation through the servers so that the clients can find that authoritative service kind of at the edge of the network. But then that authoritative service doesn't have to serve up static answers. It could serve up these, real-time steering answers and totally change the way that the entire crowd using this application is behaving from the edge. And you would normally think, I have to control this from the core of the network, and yet this architecture doesn't require that. In fact, it empowers the edges tremendously.
And another way to say that is that the DNS servers are not special in any way as far as IP and UDP and TCP are concerned.
Yeah.
They are just other servers on the network.
Yep. They're very important. They're part of I remember it used to bother me when the DNS would be down. Like maybe my local DNS server wasn't working and someone would say, the internet is down. It's like, no, the internet was still there. You could still send messages around. The DNS wasn't working right that day. But at this point, if the DNS is down, the internet is kind of down, because
effectively down.
It's so central to how clients and services find each other, how they validate and authenticate each other. And so this is the other maybe kind of big add-on, is it started as, let's give names to computers so that we can find the IP addresses of those computers. But as you said, it's kind of like the phone book. And when you think about the phone book started to host all kinds of other things. You had the yellow pages, you have advertisements, and here in the DNS, it's a distributed, globally accessible database that everybody agrees is authoritative. And that's a tremendously powerful thing. And so you don't just have to put names and IP addresses in there. You can put here's my mail server, so you can send me mail. Here is, in fact, a policy to tell you how to authenticate mail I sent you, so you can tell if I actually am the one who sent it or if it was spam, like if somebody spoofed it.
Yep.
Keys, public keys to say, this is what my signature will look like. And other what are called resource records are now, when somebody needs to put something somewhere that the rest of the world can find it and associate it with an internet property, they put it in the DNS because it's there and it works.
Yep. Including interesting use cases like proving to a third party that you actually own the domain name that you claim to own.
Yeah.
Pretty cool stuff.
And so it really goes up to, if we think about the trust model of the internet, the crossover between sort of the real world and the digital world when it comes to like identity essentially happens in the DNS. So in the real world, I could register, I'm a registered person, I guess, but also I have a birth certificate. But then if I have a company, I registered that company and, there's a legal entity associated with it. And the way I transferred that identity into the digital world is essentially that I register my domain that has effectively the same name or associated name to my company. And then all of my digital company identity information is going to go through that registration. And so like you said, if I want to prove that I am like an agent of my company in the domain space, I'll often be asked like, I want to register something. And they'll say, okay, prove that you own this domain by putting this, secret string that we gave you, this effectively one-time password, into your authoritative name server. We're going to query it. And when it shows up, we'll know that that means you actually are in charge of that domain. And that means you are this company. And that means we do trust you. And it's pretty crazy, but that's in fact how, we can talk about another time when we talk about TLS, but that's one of the ways that you actually make yourself appear to be trustworthy on the internet.
At least that you are who you say you are.
At least you are who you say you are. Yeah, so I can trust you to that point, and then, your mileage may vary after that.
Yeah, exactly. All right. What else is there about DNS?
I think we covered most of it. We did emphasize UDP. DNS can also support TCP. And so most clients will default to UDP because it's simpler. But as the DNS records grow in complexity, more are sometimes using TCP because they can't actually get the whole response in one message, or there are other reasons. So it's not categorically always UDP, though I think the majority of traffic still is. I guess another thing, just like everything else in the 1970s and 80s version of ARPANET and the internet, the original DNS had no concept of security or privacy or authenticity built into it. It was all trust. It was all, of course, whatever you say must be true. And, gentlemen don't read each other's mail, so no one's worrying about privacy. And in current internet, all of those things have changed. So there's still not a lot of privacy when it comes to DNS, but there are mechanisms to make your DNS queries private, and those are slowly gaining traction. There still is a surprising lack security and verification of the authenticity of the answers that you get from the DNS. There are protocols for that as well. They just haven't been widely deployed or adopted yet. So I think over time, the answers to those will change. Over the next 5 years or so, it'll probably become a much more secured, authentic, and private experience. But today, a surprising amount of DNS traffic is what we would say is in the clear, meaning all the routers that those queries and responses pass through can see their contents. And there's really very little verification other than just trusting that you got the right IP addresses and they gave you the right answers.
Yeah, and interestingly, you might think, well, when I go to a website and I see that it's HTTPS with a little lock icon and everything says it's secure, you might think that gives you enough protection from other people knowing that you went to that host name. But in fact, the DNS query that was made before the browser navigated to that website's IP address probably included the host name in clear text.
Yes.
So you can probably, a snooper could intercept that and know you went there. It is simply not encrypted.
Yeah.
Most of the time. I think that, like you said, that is changing, and I haven't really monitored the state of that, but I would not be surprised to find that some of our modern browsers are doing a better job with that.
Yeah, I think it is changing. And you're right. There are certain browsers, certain device vendors that are more privacy forward, and so they tend to lean into this faster. Though even the default implementations of TLS do still leak the name of the service you're connecting to. There's a way to hide that, but the initial implementation, because you might be connecting to a CDN, going a little off in the weeds here, the CDN needed to know which certificate set to use to negotiate. And so it had to be told in the clear before it had negotiated an encrypted connection who it was. Mm-hmm. And there is a way to hide the service name behind a layer of encryption now, but I don't know what the adoption is there. But if you were on the DNS side, if you were steered, it used to be there were DNS attacks that would just give you the wrong answer. Like imagine that local resolver, that recursive resolver just gave you, the name of my website instead of where you're trying to go to. And then maybe I spoof a copy of it, but I steal your information in the process, or I serve you my ads and collect pennies. And that there was, before TLS, the way that we secure the client server connections for web and other traffic, there really wasn't a way to be sure that I hadn't been misdirected. And so the nice thing, at least now, is if the trust system is working properly, when you do get that end-to-end, yes, this is a secure web connection, that does include verification that you actually connected to an authoritative server for the website you tried to get to. And it's not perfect, but it's a lot better than when there was nothing in the way trying to perform that authentication.
Well, speaking of bad actors in DNS, it's also kind of a fun bonus fact that DNS, because of some of this trust issue or lack of trust issues that it has been abused by bad actors to hide secret information. And it's a particularly good vehicle for that because almost every corporate network in the world allows outbound DNS, so UDP port 53, because it's necessary to get names resolved so your employees can go to websites and do their jobs. Now, having said that, I think a lot of corporate networks have shut that kind of thing down, and they're like, look, we will do our own DNS internally, so we don't have to allow outbound DNS. But imagine if you were you had some Trojan horse that was installed on some corporate laptop that, unbeknownst to the owner, and it was secretly sending data out to a fake DNS server with queries that just look like DNS queries, but actually contain proprietary information that belongs to the company. This has been abused in the past for that very kind of nefarious deed.
Yeah, exactly. Yeah, it was very commonly assumed that, well, like the table stakes for connecting to the internet are that the DNS work and that web browsing work. And so, network administrators might lock all kinds of things down, but they tended to leave those open. And then just for whatever reason, it seems like the next focus on filtering was, okay, let's make sure that the web traffic is going to places we approve of. But DNS was often kind of left wide open. And I think nowadays more network administrators are savvy to that. So like you said, they might have like a dedicated internal DNS server, and that's the only one that's allowed to connect outside. But that's probably relatively recent. Yeah.
All right. Well, have we explained it sufficiently well? Have we fully explained ourselves?
I think we have. I think, it'll be interesting to kind of move our way up the protocol stack from here. But at this point, we've talked about how, going back through the telecom series, how computers connect to each other and exchange information, how they exchange and build networks to send messages to each other. And now we talked about today how we can use human-friendly names in our end hosts and yet resolve all of that information into the numeric addresses needed to make connections. And at this point now, from an internet perspective, we have connectivity between all the computers, but we now actually know how to reach and find the computers we want to connect to. So I think in future episodes, it could be interesting to talk about how, once we've figured that out, how those computers actually exchange the information that we as the users care about, like web pages and so forth.
Very cool. And I'll just add one bonus fact. You mentioned that DNS's purpose is to have human-friendly names, and those names have gotten even more human-friendly in not too long ago. I think maybe 2017 or so. The Internet Association of, the other one, IANA, the Internet Assigned Numbers Authority, not to be confused with ICANN.
Yep.
They approved many new top-level domains, and now there's over 1,500 top-level domains. So it's not just governments anymore. It's everything from .basketball to, what else?
.horse, you name it.
.zippo. I was trying to do A to Z.
Oh, nice.
From .academy to .zippo.
There you go.
1,500 different top-level domain names. And thanks to some clever hacking with a system called Punycode, there's actually a way to have emojis in your DNS names. Which is kind of a hack, but really fun that you can do like iheart.ws, and that is actually a valid website that demonstrates emoji domain names.
Yeah.
Not very practical, but really fun.
Yeah. Though that's based on a very important technology, which again, the original DNS, very American-centric, said, if you've got the US alphabet, letters, numbers, and hyphens, what more could you possibly need? And the answer to the rest of the world was a lot more than that. So, the idea with Punycode was, and it's a pun off of Unicode, which said, let's find a way to encode the entire global character set called Unicode into a way that the domain name system can handle it, even if you don't have to upgrade the servers. And that way you could have domain names in all the languages of the world, which happen to include emoji. That's in fact the language of the next generation. So
the Gen Z language. All right. Well, Shane, I say fabulous job explaining ourselves today. I think we deserve a pat on the pat on the back. And I hope all your DNS queries resolve fully and quickly and authoritatively.
That's right. Thanks a lot, Dave. May you have happy eyeballs.